Something to Chew On is a podcast devoted to the exploration and discussion of global food systems. It's produced by the Office of Research Development at Kansas State University. I'm Jay Weeks, PhD candidate in the Department of Agronomy. My co-host is Scott Tanona, an associate professor in the Department of Philosophy who specializes in the philosophy of science. Welcome back, everybody. Before I introduce today's guest, I have a quick ask. If you're enjoying this podcast, please leave us some ratings or comments on whatever platform you happen to be listening on. We'd love your feedback on to how to make the interviews more interesting or useful to you. Scott and I are really having fun with these conversations, but ultimately we want to make sure that we're serving you, the listener. So please, we'd appreciate it if you took a couple minutes to do that. For today's interview, Scott and I had a great conversation with Dr. Melanie Derby. Melanie currently holds the Hale and Mary Segal Professorship in Engineering, where her research focuses mainly on thermal fluids problems. She is part of the newly founded KSU R3 NRT team that's looking to leverage interdisciplinary collaboration to tackle some of the greatest challenges at the food, energy, and water nexus. Most of our discussion covers how an engineer thinks about improving water use efficiency in both the agriculture and energy sectors, but we also talk a little about Melanie's experiences in science education as well. Hope you enjoy. Today we're fortunate to have Melanie Derby from the College of Engineering and the Department of Mechanical and Nuclear Engineering here to talk with us. Welcome, Melanie.
Thanks, Jay.
Melanie, so we'll have introduced you briefly just before starting the podcast here, but in your own words, what's a little bit about your background?
I'm a mechanical engineer by training. I have a bachelor's degree in mechanical engineering from Rensselaer Polytechnic Institute, as well as a master's and PhD. And my area of expertise is multi-phase flows. So liquid flows, liquid vapor flows, vapor liquid flows. So, primarily in condensation as well. So this is like when you're taking a hot shower and you notice the mirror is foggy. That's because it condenses.
Happens to me every morning.
Yeah. And so that's a process that we study a lot.
So how did you get to wanting to study multi-phase flows and things like that? Is it something from when you were a little girl? Is that what you always wanted to do? Or?
Well, I grew up in a family of engineers, which of course meant I didn't want to be an engineer for a while. But junior year physics kind of set the course. You know, I started doing extra problems, homework problems for fun.
You were doing extra physics problems?
And my father said, that's not normal.
Depends on how you define normal.
True.
So from there, you decided that you wanted to pursue physics, or what got you into the engineering side of things?
I think physics and mechanical engineering are both great fields, and I think both have different options. For me, I really liked kind of the engineering mindset that you're using math and you're using science, but it's applied to solve problems. And I think the idea of solving problems is really what excites me, in my work today with my students and our great research teams. We're really trying to solve problems. That's really the heart of what engineering is.
So would you describe that as sort of more content-based, like sort of there's this thing that you study and then you look to see what problems you can solve, like given that, or are you driven more by the set of problems? Right.
I think everyone has their own process. Mm-hmm. For me, I like to look at what's a real problem and then start from there and use kind of our skills and our knowledge to be able to apply that to the problem.
So have you gotten into new areas of research like because of that, right? So you found a problem and said, oh, there's something that we're not studying yet, and you got to start figuring that out?
Exactly. I mean, my background is in heat transfer and energy, but I
pretty broad generally, right? Yeah.
I didn't have an agriculture background. Then when I came to K-State, I started seeing all of these heat transfer and energy problems and how they interacted with sustainable food systems. And, that's kind of where that research match was made. One of the things I just really enjoy learning.
Yeah, so that's neat. When you first started talking about your research area, it didn't sound immediately like agriculture or sustainable foods at all, right? So, right, is that and I know you've got some new projects that are particularly in that area, but has this been a shift for you?
I think it depends how you look at it. So something like condensation, you might think, how does that really relate to food systems? But it's extremely important in power generation. Every, fossil fuel power plant requires a condenser, and condensers tend to be pretty large and therefore pretty costly. And so you're always trying to figure out how can you condense better. And kind of the starting of this research is looking at kind of the competition between agriculture and energy for water. When energy is a pretty large water user, 40% of water withdrawals in the U.S. are to produce power. Now, only 3% of consumption is from power plants, but that withdrawal rate is important. And you start looking into power generation. You know, we all like to charge our iPhones and you know,
record podcasts.
Right.
You know, obviously electricity is wonderful, but in semi-arid and arid regions, especially, power generation is a challenge.
So, just for people who are curious, what exactly kinds of power plants use water, and what are they doing with that?
So you know, the whole goal of a power plant is like, you know, the old school water wheel, right? You might think about on the river that you're just trying to spin something, and you're spinning it, producing kinetic energy, and you're using that to generate power. Now, in the modern cycles, you're using a turbine to spin. But it's essentially like a water wheel. But you have fluid, which is usually water, flowing through the cycle, and it goes through the turbine as a gas, and then you have to condense it back to a liquid so you can send it through again. And so that's the link to the condenser.
So that's why it's only using 3%, but there's a lot of withdrawal as a result of that, right?
Right, and you know, in the early days of power generation, you would just put your power plant right next to a river. You'd pull in river water, you'd heat it up a little bit, and then you'd send it back to the river. That's the once-through condenser. But for environmental reasons, you know, that's no longer the standard. And so that kind of means that as engineers, we have to look at different ways to tackle this problem.
Nice. Yeah, that's interesting. So I guess moving back to the agricultural aspect of things, what kinds of projects are you working on in relation to water?
So one important process in terms of growing crops is the idea of evapotranspiration. So you have some evaporation from soil, and you have some transpiration from plants. So just like we sweat to cool ourselves, plants transpire to cool themselves. So it's really a cooling process. So that in and of itself is heat transfer. And the evaporation process, that's a phase change, right? You're going from a liquid to a vapor. And that's really where the mechanical engineering tools and skills we have relates. And so we're working on some projects with, sponsored by the National Science Foundation. One is a National Science Foundation research traineeship, R3, Rural Resource Resiliency, and it's a training program for graduate students. So we're looking at these idea of limited resources in food, energy, water systems, particularly in the context of the Ogallala Aquifer.
Is there a need for more mechanical engineers working on agricultural projects, or is it, I don't know, something that mechanical engineers know that they can go and sort of, you know, apply their skills in a variety of ways, including ag? So, you know, for engineers, you know, one of the things you're always doing is you're always trying to improve the process, right? But you're also trying to model, trying to predict. You know, that's where models get really powerful, when they actually represent what's happening. And so some of our mechanical engineering expertise can help us make better models in terms of evaporation. You know, so I think that's a strong link. Mm-hmm.
So is this something you're showing to farmers, or, you know, how do you make that link from doing the academic work to putting something into practice in the field?
We collaborate. But in all seriousness, I think you have to work as a team, right? Once you get a large enough problem, you have to work together. Everyone brings their own expertise. There are challenges with that kind of teamwork, but I think it can also be really fun and really fruitful. And as part of our R3, one of our co-PIs, Jonathan Aguilar, is at the Southwest Kansas Extension. And so we're going to be sending faculty and students, and he will host us for a week every summer where we'll get to meet the farmers. Our trainees will be doing sociology, research. They'll be doing economic research, trying to ask people, what are the barriers to implementing new technology? As engineers, I think we have a lot to bring to the table in terms of our technologies we can develop. But we really want to understand and work together with our social scientists to understand how are people going to use these technologies.
I mean, you just highlighted a really important part of engineering, right? Which is the sort of, if you're going to apply it, you have to know what you're applying it to, right? And sort of what the interests are and what the needs are and how it's going to get used. And I think sometimes people can forget that that's a crucially important part of any sort of engineering project, right? So I want to ask you more about that, but first I want to just sort of see if I could get a sense of kind of specifically, like a little bit more, like how the mechanical engineering bit applies to some bit of like plant not perspiration, transpiration. I'm just screwed it up. Evapotranspiration. Wow, how about that? All right, sort of like there's a reason I couldn't think of that word, right? So are there particular issues that you're already aiming to try to solve, or you know that there's just a complex of stuff that you could find and start working on?
So it's a great question. If you go to the grocery store and you go to the vegetable counter, right, and you see, they miss the vegetables every once in a while. Yeah. And you want to have a good time, like spend 10 minutes at the vegetable counter. And, it's a great time. Yeah. But what you'll notice is that the water droplets don't look the same on different types of plants. So on some plants, the water will really spread out. And that's something we call a hydrophilic surface. It's water loving. The water really spreads out. Then you look at, say, broccoli or cabbage. The water beads up a little more. Right. For the cabbage, it's mostly because it's a waxy coating, but for the broccoli, part of it is because of different textures, so that the different textures help it be hydrophobic or water-fearing. And so this is called wettability. So you have hydrophilic, water-loving, hydrophobic, water-fearing. And
so affected both by some of the properties of the plants, but also then how we treat them and preserve them and wax them or whatever, right? Okay.
Right. And so our ideas are looking at how can you tailor soil wettability to reduce evaporation.
Gotcha. For the soil, not for the plant now, right?
Not for the plant, right. But I think the plant, those are examples.
It's a really good example, right? Yeah, that's right.
Sure. So will this be something that you apply in the irrigation water, or will you apply it to the soil before you start irrigating, or both?
I think we will soon know the answer.
Stay tuned.
And I think the answer will probably be a combination.
Sure.
But I have an NSF career project where we're looking at this. And one of the things that's really great about the National Science Foundation is you can start looking at a little bit more of a basic science level. You can start asking these really big and good questions. And then once you have the answers, you can tailor it. How do you apply it in the right way? So I think we need to understand a little bit more first.
Yeah, you bring up a good point, right? Not everything has to be immediately applied to the field, tomorrow. It could be 10 years down the road, but, if it makes progress, it makes progress.
Right. It's an important part for everybody to understand in terms of how science works in solving our communal problems, right? Sort of there's a lot of basic science that has had all kinds of interesting applications that we didn't even know about from the beginning, right? Yeah.
And sometimes part of it goes back to what kind of models do you have, right? You have to take the time to develop the models, sometimes use computers, sometimes use experiments, kind of our general equations. So these are all important aspects, and, you
need to do this theoretical work, right? Sort of before you can start applying it, right?
But I think it's really also important we have that application in mind.
Right.
Sure, you got to have something to truth the model against, right? For those who don't know, what exactly is a model? Like, how would you, in basic terms, what are you doing when you're developing a model?
That's a really big question. It's complicated, right?
I mean, we're not asking you to scribe down calculations, right? But
so I guess, let's think about, I think many people have grown an office plant or killed an office plant or have gardened, right? Have tried to grow a plant.
I have never killed a plant. I'm an agronomist.
I've killed lots of plants.
So you think about what are the factors, right?
Sure.
Temperature. Is it hot or cold? That's going to affect how much evaporates. Wind speed, right? We can have pretty windy days. That'll affect evaporation. How sunny is it? And not only how sunny is it, but what time of year is it? Just think about, there are times of the year you can get a sunburn really quickly, and there are times of the year that it just takes longer. So these are all kind of factors that go into our modeling. And we're doing experiments, we're doing modeling, some simulations down the road. So when you're making a model, you're trying to figure out, how do the different factors like sun and wind and temperature affect your outcome, evapotranspiration.
And a model is then, the set of those factors and conceived a particular way too, right? And then sort of what you think the interactions are between them, right? And so you can't always test a model directly against the world, because like the way it says you're modeling it, right? So you're coming up with a particular way of conceiving the world, right? And then you're going to see if that works. Yeah.
Yes.
Nice. Yeah. So, there can be huge, complicated models, but there also can be simple models that help you understand specific small components of the system, right? So, you said part of the project is based out of southwestern Kansas, right? And you mentioned the Ogallala Aquifer. So, why is that such a problem, and how does it relate to all of this?
So, the Ogallala Aquifer spans, I think it's 8 different states, and it's a key irrigation source for many states, including western Kansas. And so it's now, based on the predictions you ask, I think the general consensus is that it's decreasing, right? And there are some questions on the rate of how much it's decreasing, but the general consensus is it is decreasing. And so, we think that we need some engineering innovations, and we also need some socioeconomic innovations to kind of help sustain the system, right? The Ogallala supports a lot of agriculture, right? Irrigation supports yields. So these are all important factors.
Has rate of use been increasing too?
That's a very complex question.
Right. Okay. Mm-hmm.
Yeah, I listened to a presentation the other day about it, and some of the laws and things that have surrounded, been around for the last 100 years make use of that source super, super complicated.
So I want to ask, sort of for big things like this, so I think it depends for the answer to this, I know, is going to vary depending on sort of the particular situation. But there's been a couple of times now we've talked about socioeconomic, social factors, right? Sort of economic factors and technical ones, right? So when you engage in, engineering project, either sort of in the beginning or, once you're actually getting down to some nitty-gritty applications, how much those different factors weigh, right? A lot of times I think people think it's easy to come up with a technical solution for something. Well, first of all, it's not easy, but then second of all, even if you have a technical solution for something, it's not a solution unless it gets applied in the social system, right? So, how do you think about sort of the interaction between all these different factors?
I think part of it depends on what's your goal. Are you a company and you're producing a product tomorrow? Are you in academia and you're doing research? So research is creating new knowledge. And the question is, when will it be applied, right? Something that might not be economically viable now, in 5 or 10 years could be. And I think one of the advantages of doing research is you have that knowledge and you're building towards that. And I think that's one of the advantages also of being in academia, is that we can think in a little bit of a longer time scale than some companies, right. And that's one of the goals of, in my opinion, government research, is to, plant the ideas, develop the technologies, and things can always change down the road.
Oh, yeah, certainly. And if you develop some sort of new substance or something, there's no market to make that substance on any sort of scale, right? So that's what will help to drive the costs and things like that down in the future. So you mentioned you're gonna be doing a lot of graduate student research training.
Yes.
How in an interdisciplinary program like what you guys are developing is that different than a traditional graduate student experience?
So all of our graduate students will get their degrees from their home department. So mechanical engineering, sociology, chemical engineering, for example. But we're introducing some interdisciplinary graduate courses. And so part of the training will be from these interdisciplinary courses, a capstone design course where the students will work in kind of interdisciplinary teams to solve real problems. So that's a little more on the applied end. And we're really going to be asking stakeholders, for example, farmers, producers, to give us some of their problems, because we really want to be solving current problems. So that's on the coursework side. And on the research side, we have different research teams that we're bringing together. And the team will be working on some more of that basic research, right? Increasing our understanding, increasing our models, and being able to use that information in the field.
So do you have a core facility for all this to be going on, or is it all going to be happening in respective labs in different departments and that sort of thing?
It'll be in respective labs, but we're working together.
Sure. Yeah, and you are just bringing on a new cohort of students, right?
Yes, so our first cohort will start in August.
Oh, great. How
That's
many
exciting.
students?
So we'll have 18.
18. Great. Excellent. That'll be interesting for them all to be starting right at once, huh? So you have some experience with other types of education, right? You were involved with the GK12 fellowship when you were at RPI, right?
Yes.
Yeah. Tell us a little bit about that and how it's contributed to getting you here.
So the GK12 program was a fellowship sponsored by the National Science Foundation, where they would send graduate students into middle and high schools in the local community. I really had a great time. I worked with Carl DeCesar, and
And you were a fellow.
I was a
So
fellow.
yes, right.
Yes, I was a fellow, and so I worked with a high school teacher, a middle school teacher in the technology area. So he taught technology classes. Actually, he still teaches them. And working with students on kind of technology and pre-engineering education. And this was a really great experience for me. Time to really learn how to be an effective teacher, how to interact with students. And I think you're always asking, why are we doing this, right? Students always want to know why, and I think it's important that we know why. And you laugh.
They can sense it, right?
Yeah.
You know.
Yeah, teaching's one of the hardest things, right? You have to actually be able to answer lots of questions. So NSF isn't doing this GK12 program anymore, I think, right? Yeah.
Not anymore, but as part of most NSF projects, they expect the researchers will also be contributing to education.
Mm-hmm. Right. So I was involved in one of these too a little while ago here at K-State, and I know that one of the goals was to not just get the graduate students sort of better at teaching and better at communicating, but part of the vision, I think, was that it changed their view of science, partly, because teaching, you have to really think through things. Did it have an effect on you that way too? Like you rethinking kind of what you were up to or why it was important, or answering some of those kind of out in left field why questions?
I think it gives you a different perspective, and that's, in my opinion, always a good thing. It's one thing to sit in the lab with your peers who understand everything about what you're doing and talk about your work, or your faculty advisor who understands. But it's another thing to talk to someone who's a ninth grader and who's really interested in what you're doing, but maybe hasn't taken the same courses yet, doesn't have the same perspective, right? But you still want to be able to bring them in, right? To show them what's cool, what's exciting, how this can really make an impact. I think in terms of research, one of the big questions is, how can this make an impact, right? And we have to do this basic science. We have to figure things out before it can make that strong impact. But how do you communicate this to other people, I think is really important. And that was something I learned from GK12.
That's excellent. Were you always interested in teaching and kind of engagement and making sure the work is eventually applied to, or is this partly also influenced, do you think, by that experience?
I would say I had an excellent graduate training experience. I really respect both of my advisors, and I think they taught me very well, and I'm continually thankful for that. And so our research group was a more interdisciplinary group. And so in our research meetings every week, we were having these conversations, and I think we all benefited from these different perspectives. So I liked that aspect of my graduate research, and then I think the GK-12 just added to that.
Mm-hmm. That's great. And this new project is partly a graduate training program too. Sort of broadly, do you think there are major things that we need to be adjusting in graduate education, like more interdisciplinary, more engaged? Do you think we're doing a good job in general? I mean, what's your view about the status of graduate training in general in the sciences and engineering? It's a big question. Sorry, it really put you on the spot, right? Sort of, but
take your time.
Yeah, right.
So I think there's a lot of good, and there's also a lot of room for improvement.
Mm-hmm.
I think the good is that faculty mentors care very much about their graduate students and have a lot of one-on-one mentoring. And this is something you may not get in an undergraduate experience that you get as a graduate student. And so I think that is really a huge benefit of a graduate degree. One thing that we're going to do is to have different graduate mentoring as well. So that as a graduate student, you'll have faculty mentors from outside your department. And one reason is we really want, sometimes an outside perspective can be a good thing. It can help you get a little unstuck, but it can also help you think about, what are my career goals? So we want our trainees to be thinking about what are their career goals earlier on in the process rather than, pretty right up to when they're graduating.
Yeah, when they're defending. Right?
Yeah.
Are there some common traps that you see that graduate students falling into that you're trying to fix in this program, besides thinking about a career too late?
We're also interested in training graduate students to be good science communicators. That is an important part of life. And particularly engineers, it doesn't matter how brilliant you are if you can't tell someone else about it. And so, sometimes what we do in engineering is fairly complex, but to be able to distill that down to what's important and be able to communicate it to someone else is a skill.
It is. It's a hard skill to learn sometimes, right?
But the good news about it being a skill is you can learn it.
You can learn it. Mm-hmm.
So will you have like field days and things where your graduate students can go out and talk to different stakeholders, or what's the mechanism of disseminating that information?
We have a whole bunch.
Sure.
I'll highlight a few. One is a seminar series, both to invite people on campus, but also external speakers, and as well as some of our own team. When you're doing interdisciplinary work, it can take some time to understand someone else's vocabulary.
Sure.
That can be a real challenge. It sounds silly, but it can be a real challenge.
Huge, right?
So that's part of it. Other things there are some great things sponsored by the graduate school in terms of professional development. There's the 3-minute thesis competition where you get to present your thesis in 3 minutes. And that may sound easy, but it's actually challenging because you have to think about what's the most important thing to someone outside my field and how can I explain it in 3 minutes. And then we're also sending them to Topeka to meet legislators who are doing water policy, as well as to Southwest Kansas.
Yeah, what do you think about the elevator pitch or the 3-minute thesis concept? I've always been a little bit skeptical, I'll be honest, because if you distill things down too much, then you sort of lose the value of it, right? So, do you think it's good to be able to condense it down to just a couple sentences or whatever, or how valuable do you really think it is?
I think the thing that transcends may not be the exact science and may not be the exact equations, but what transcends is why you're doing it, and I think that's where the impact plays a role. I could, go on for the next 20 minutes talking about my favorite equations, right? I won't, but I could.
And we know you've got some,
this is a long format podcast, right?
But I can tell you why we're doing the work, right? Why we're concerned about water usage in power plants. Why we're concerned about how to work with power plants to reuse water in their plants, why we're concerned about evapotranspiration, particularly in southwest Kansas when a substantial amount of irrigation happens. And so I think what transcends is the why. And so the elevator pitch, I don't think, has to involve all of the equations, but some of the basic ideas and also why we're doing this research.
It's easy to get hung up too much on precision, right? So you're going to lose precision, right? But maybe you can get the accuracy, right? And sort of and accurately describe what you're up about, what you're trying to do. That's really important. So I was wondering if we could get back to some of the science. We've been talking about some other things that are really interesting, but I don't want to lose out on some of that. I know at the start of a new program, there's this interesting spot that everybody is in where you've got a bunch of research and plans and ideas of where things are going to go, but then this is the way science and engineering works. It's open-ended. You don't know what's happening next, right? But I was hoping you could say a little bit more about so the soil evaporation, sort of like what's going on there. What are you actually trying to solve?
So we're looking at our fundamental hypothesis is how can wettability affect evaporation from soil?
Right.
And the idea is that once you know how it can affect it, then you can figure out how you can tailor it in the way you desire.
So the open questions still are about how it affects evaporation, okay?
So will the wettability prevent evaporation, or will it help get water deeper into the soil quicker to prevent it that way?
A little bit of both. So when you have I have a potted plant in my office, and happily it has a glass wall, so I get to watch it. So you fill it up, right?
Cool.
You fill it up, and you have soil particles, and then there's space, right? And the space can be filled with air or it can be filled with water. And as time goes on, from the top layer, you have more and more evaporation. So that first stage of evaporation just happens at the top layer. Water is in contact with the top, and it's just about what's the sunlight, what's the wind, what's the temperature. And that's going to govern how it evaporates. And so wettability kind of on that top layer can affect how the water beads up. And we've done some studies simulating a soil pore in controlled environmental conditions. And we have one that is glass and one hydrophilic. And then we have one that's Teflon, hydrophobic. It takes longer to evaporate from the Teflon one. Kind of the next level is looking at, once you dry out that top layer, you have to pull water in to evaporate. And that's called liquid capillary transport. So how the water motion in basically these really small channels can be affected by the wettability
soil, right? Yeah,
between the soil particles.
Yeah.
And so we're doing work right now. My graduate student Partha is doing some great work on that right now. We're collaborating with Hitesh Bindra in nuclear engineering. So we're using X-rays to figure out where's the water in the simulated soil as it's evaporating.
Nice. So to cover the capillary action quickly, so the water at the is equal in the soil profile, and then as it dries out at the top, it's it's wetter below and drier above. So the water goes from where it's wet to where it's dry, and that's capillary action.
Yes.
Right. So in the simulated soils, are these like glass beads? Are they Teflon beads, or like what are they? Varying size distribution? What's the experiment look like?
So right now we're trying to do our best to control the parameters, and so that's why we're using beads rather than actual soil.
Sure.
But we are planning in subsequent years to kind of scale up to soil with known pore size distributions. But right now we're using these simulated soils. So we have glass beads, and then for these latest experiments, we've coated the glass beads with a very thin Teflon layer. So the diameter is about 2 millimeters. So that thin Teflon coating doesn't really change the diameter in any appreciable way. But when you're designing experiments, one thing you have to do is you have to think about what are you controlling. If we just use Teflon beads for these experiments, they have a different specific heat. And so they absorb heat differently. And now we're not comparing apples and apples. Now you don't know, is it wettability or is it the different specific heat? And so that's why we had an excellent undergraduate who is persistent, helped us coat these beads. And they turned out great. They're looking really good. But we needed to be able to control control the conditions.
That's a interesting bit of science, and sort of for our audience thinking, who are in a whole range of some people very scientifically familiar with science, and some people listening from all kinds of backgrounds. So that control, you've got these sort of very simplified models in some sense, right? But part of the idea is if you don't do that first, right, you're just dealing with such a complex situation. You can't sort of make any progress with that, right?
Right, and it is, in my opinion, more beneficial to start with a simpler model and really understand and really be able to say why this is happening, rather than saying we have 3 options why evaporation is lower, but we can't tell you which mechanism, right? Our whole goal is to really understand these mechanisms. Once we know the mechanisms, we can work with people like Jay to implement it in the field. But if we don't know the mechanism up front, we could guess.
Right. So what's the third one?
So the third one is enhanced vapor diffusion. So
you're going to want to explain that.
Yes. So
for me,
my favorite example of a vapor diffusion is say I'm cooking hot dogs on the grill, and you're on the other side of the deck. I put the hot dogs on, I close the lid. Do you smell it immediately?
No.
Not immediately.
Not immediately,
Yeah.
right?
Right.
But at a certain point in time, you're going to get a whiff.
Right.
And you're going to say, oh, I smell hot dogs.
Right.
Right? That's diffusion. It's a very slow process. It doesn't happen immediately. It doesn't have a huge velocity. But the particles just make their way to a different position. And so what happened is there's some early work in the 1950s where people did experiments, and they had pretty good diffusion models, and they said, our evaporation in soil is like 5 times greater than what we'd expect in our diffusion model. Why? And part of it is because you have these soil particles, and you would form these liquid bridges between them. So you'd have 2 particles and then a liquid bridge in between, and that would kind of accelerate the diffusion process. And so
because there's greater surface area,
it's actually pretty neat. On one side you would evaporate, and the other side you'd condense. So that basically instead of diffusion, you have an actual phase change. And
Interesting.
why we like phase change heat transfer is it's usually more effective. So wettability can also affect this vapor diffusion, we think, right? And we're going to investigate it because it can change the shape of the liquid bridge. And once you change the shape, and how the shape evolves is really important for saying how the evaporation actually occurs.
so you're looking to slow this process. Yeah. Interesting.
So that's really neat. So that's one part where your research area sort of applies to soil, water, evaporation of water in the soil. You're also talking about energy. Could you say something else about what's going on there?
Great. I mean, our interest in energy is, heat transfer is really at the heart of most energy generation, most electricity production, and also this competition for water, right? So there's a few areas where this really starts playing a role. So if you are in a dry area and you can't reject to water, so you can't use water for your condenser, maybe you don't have the water, or it's salt water and it's really going to be very corrosive. So you say, okay, we can't reject it to the water. We will reject the heat. We will transfer heat from our steam cycle to air. The problem is you're doing that, and you can only get the steam to the temperature of the air. So if it's 95 Fahrenheit, that's the lowest temperature you can get the steam. But then in thermodynamics, we like to think of something called the Carnot efficiency, which is the kind of maximum, like best case scenario for efficiency. And it's related to the condenser temperature. So it's 1 minus T condenser over the boiler temperature. And so if you have a higher condenser temperature, now you have a lower efficiency. And the worst thing is this happens on a hot day, and that's when you have the greatest electricity demand, because everyone wants to run their air conditioning.
But then the least efficiency then if you're using air, right?
So this is an example of where it really plays in. And we've done some work in condensers, but one project I wanted to highlight was looking at recovering water from cooling towers.
Okay.
So this is an NSF project. Stacy Hutchinson in Bio and Ag is working with us on this one. And so have you heard about the fog collecting billboards?
The fog collecting billboards. No, I don't believe I
Oh,
have.
okay.
So tell us.
So in certain areas of South America, there's a billboard that says, this billboard collects water, right? So it's the whole idea of dew point, right?
Mm-hmm.
You have some moisture in the air and it condenses overnight because the surfaces, maybe the grass cools, right? You'll notice condensation, dew on the grass, but you won't notice it on the sidewalk, for example.
Right.
Sure.
So you have this condensation happening from this air. And there's this group who, a couple of years back, took this idea of a fog collecting billboard and they just put it in a cooling tower of a power plant.
They put the whole billboard in the cooling tower?
Well, they put basically,
Yeah.
essentially that's what they did.
Okay.
And they were able to get back a lot of water that otherwise would be lost. So when you drive by a power plant, you often see a cloud.
Right.
That cloud is
Yeah.
It's just water.
water vapor. And so we're looking at ways that we can get the water back.
So before it escapes there,
Mm-hmm.
condense it down. So this isn't a standard part of plant energy production? Yeah.
It is and it isn't.
Yeah, okay.
Our approach is a little bit different. So we're looking at how could you use. So if you're, one way is you can condense a droplet. Another way is you can just capture a droplet that's in the air. Mm-hmm. And I think both have their pros and cons. But this fog collecting billboard was essentially just a mesh. Like think of it like a fence. Okay. And they just collected water basically from the fence. But our idea is that if you can change the wettability, either all of it or selectively, so again, that wettability link, and you can shake droplets off, that gives you more room to get new droplets. And it can increase your efficiencies. And so we're looking at, how do droplets move under some shaking, under some vibrations? And Stacy's working with us. We're testing water from power plants, and we're looking at how water quality can affect the droplet motion too. And so I think this is really exciting to me because I think it is interdisciplinary, right? We're all engineers working on this project, but we're looking at it from different angles.
Right.
We're looking at it both from that scientific standpoint of what are the mechanisms of making the droplet move, but also moving towards the applied. Once we have this water, what can we do with it inside the plant?
Right. So this sounds like it's closer to the applied side, right? Sort of
Mm-hmm.
it can be you're not as far down the pipeline from being able to actually bring this in to the applications. Cool.
What are some of the water quality issues that may be apparent in something like this?
So you can have, it all depends on your source, right? Salt water, the salt can leave deposits, and we call that fouling. It's a foul name, right? But we call it fouling.
Yeah. Sure.
And so you can have salt water. We've done some tests with like a simulated seawater. We've done some tests with cooling tower water, other power plant water sources. And so we're looking at, so with these different water qualities, it can change the properties of water. So it can change your surface tension, it can change viscosity, and it can change density. So you're changing those fundamental parameters, that's going to affect how your fluid moves.
So is the idea that this water could then, once it's captured, be circulated back into the system, or would you have to dispose of it in an agricultural system or something like that?
I think all are options.
All of the above.
But it depends on what's that initial quality. There's a limit to how many times you can recirculate. But again, if you're in an arid climate or semi-arid and this helps you have a water-cooled condenser rather than an air-cooled condenser,
It may be totally worth it.
Mm-hmm.
Yeah.
So if I remember correctly, you were also working on looking at the microbial aspects of some of the water dynamics in these soils as part of the project too, right?
yes.
So what kinds of things are going on there?
Yeah, Ryan Hansen in chemical engineering is really leading this work, and he's doing a great job. And one of the things that we'll be looking at together with our NRT team and our excellent students coming in the fall is kind kind of the interactions between water and microbes, right? And one of our questions is, how are the microbes going to relate or respond to drought stress? And what are the interactions with the water and the evaporation mechanisms and how they tie together?
Okay. So are you thinking about, how you can introduce some microbes to the system and how that might impact it, or are you just looking at the native populations and how they respond to these different things?
I think a little bit of both.
A little bit of both. Great. Well, that'll be interesting. I know that the microbial and biologicals are getting to be really popular, especially in the ag industry. Time will tell what actually comes out of
under-examined
it.
aspect for a long time, right?
Yeah, sure. And companies like Indigo Ag and I think Monsanto, before they were bought by Bayer, were investing heavily in trying to understand how those things impact it. So, great.
It's all about the system, right? you can't just look at one part. And I think with the NRT, this gives us the opportunity to look at the whole system.
Sure. Do you have any final last words then for graduate students that might be interested in your program?
I think the general life advice is that you can't win if you don't submit, right? So if you're interested, reach out to our team, particularly the faculty members in the areas you're most interested to. But if you don't apply, we can't give you a traineeship.
Sure. And they can find more information on your website, correct?
Yes.
Which is nrt.kstate.edu or
nrt.research.ksu.edu.
.ksu.edu. And you'll be looking to accept more students towards the end of this year for the following year,
yes.
Correct? Great. Well, thanks so much, Melanie. We appreciate you taking
looking forward to seeing what comes out of that.
Thanks for having me.
Thanks
Appreciate
so much.
it.
All right.
If you have any questions or comments you'd like to share, drop us an email or check out our website at kstate.edu/research/global food. Something to Chew On is produced by the Office of Research Development at Kansas State University.